So our speaker for today is a postdoctoral research fellow at the Université Catholique de Leuven in Belgium. Her research focuses on the intersection of climate dynamics and machine learning, with a particular emphasis on improving the prediction of Arctic sea ice. She develops innovative machine learning models that leverage satellite observations to forecast sea ice conditions, aiming to enhance the skill of both short-term and seasonal predictions. She earned her PhD from the Massachusetts Institute of Technology, where her work centered on understanding the sources of sea ice predictability. Our speaker for today, ladies and gentlemen, is Dr. Lauren Hoffman.
Hi, everyone. It's great to be here. I'm going to go ahead and share my screen. Uh, so can you all see the slides? Are we good?
Yes.
All right. So yeah, today I'll be giving an intro to machine learning for Earth and climate scientists. And to start out as sort of a motivation for this talk, I have this image of depicting the Cambrian explosion that happened some 500 million years ago at the bottom of the seafloor. And this was just the explosion of all different types of life. And this quote here relates that to applying AI in climate sciences. And it says the figurative Cambrian explosion of AI techniques in earth and climate science, however, only began over the last 5 years and will rapidly continue through the coming decades. And so it's a really exciting time to get into this sort of application of AI in climate science. And to illustrate this further, I went to OpenAlex, which is this comprehensive index of publications, and you can type in key terms and it'll give you some statistics of how often those terms were mentioned in publications. And we can see from 2002 to 25 this huge increase in this term machine learning and climate. And I think one of the main reasons that we see AI applied so well in our field is that the Earth system has this vast and growing array of available data from a variety of observing systems. We have satellite in situ, climate model outputs, reanalysis products, and this gives us, anything from local observations to this global mapped scale of these different, atmospheric, oceanic, land, and ice components of the Earth system. And machine learning loves data. It's essentially the machine learning models learn statistical interactions and data and give us information in that way. And so in this field where we have almost more data than we can analyze as a human, machine learning fits really well. And so there are a number of applications for machine learning in earth and climate science, which include but are not limited to, improvements of Earth system models, improvements of data from satellite and observations. Shown in the bottom here is an example of using machine learning to create high resolution data sets from coarser satellite products. And then lastly, we have this weather and climate prediction, which in the image we're showing the blue lines, which are different forecasts of a cyclone track, and the red line is an actual track of the cyclone. And I think I focus in this weather and climate prediction side of things, and we'll go through an example of that later in the talk. And so as far as an overview for the talk, first, we'll get into what is machine learning, look at different types of machine learning through the lens of this case study. And then the latter part will be this question of what is the machine learning? How is it learning? What's really going on in this black box that we call a machine learning model? And we'll sort of play with that in this activity that's called the Neural Network Playground. And then lastly, I'll leave you with some resources if you want to go further and learn to build your own machine learning model. But first, I have a Slido question just to get a feeling for where we all are as far as machine learning. So I just posted the link in the chat, and I will go ahead and share a different screen now. So you can click as many answers as you want. And the question really is, how familiar are you with machine learning? The answers range from I've heard of it, I've used it, and this refers to AI tools like ChatGPT, maybe some coding aids. I've read papers using machine learning. I understand how it works, and I've built my own machine learning model. And again, click as many as you'd like, and go ahead and yeah, answer. And yeah, so as we see these statistics roll in, it's sort of the distribution is where I might have expected. We are all pretty familiar with AI and have come across it in our lives. But maybe these last two, I understand how it works, and I've built my own model, not as much. And so I hope that by the end of the talk today, we'll have a little bit more confidence in understanding how it works, and perhaps we be convinced that maybe we have built a machine learning model without knowing it. So yeah, I'll leave the Slido open, and for now, go back to the slides. And the first question we'll address is what is machine learning? And simply put, it is fitting a model to data. And so I really like this image on the side here that because I often get asked this question, what's the difference between AI and machine learning? And so AI is sort of this program that uses a machine learning model to sense, reason, act, and adapt and make decisions. So the AI is sort of the acting body, whereas the machine learning model is what it's using to make its decisions. And it's this algorithm that's learned statistical interactions within the data that you fed it. And then the smaller circle is deep learning, which is a subset of machine learning where we use these multi-layered neural networks to learn from vast amounts of data. And I put this here because today we'll be focusing on a deep learning model. And so generally within Earth and climate science, we use the numerical model. This has sort of been the state of the art until recently. And this slide sort of shows the comparison between numerical models and machine learning. So on the right-hand side, we have the numerical model. And with this type of model, the inputs that we give it some data and we give it a program. We tell it how the physics works. We give it these equations of conservation of mass momentum energy or other equations about how the physics and chemistry move forward in time. And so with this, it produces an output. As it steps forward in time, it tells us what's going to happen in response to this data and this program. Machine learning, on the other hand, we give it data. We give it inputs and outputs, and it learns some program. And this program that it learns is in the form of statistical interactions that are happening between the inputs and outputs that we've given it. And so within that machine learning, there are a few different types. I'm mainly going to focus on the red circle today, but I'll just mention the other two. There's reinforcement learning, the orange circle, where this model learns a series of actions through trial and error. There's unsupervised learning in the blue circle. And this is really useful for discovering patterns in what we call unlabeled data. And so in an unsupervised model, you give it a bunch of inputs and it sort of learns different clusters within that data set you've given it. So different sections of the data that behave similarly. And then lastly, there's supervised learning. And this is where you make predictions from labeled data. And what I mean by labeled data is now you give it inputs and outputs, and it learns some interaction between the inputs and the outputs. And so within supervised learning, we have two types, classification and regression. Today, we will mainly focus on regression, and this comes in the form of neural networks and linear regression, and we'll look at those two. But briefly, I'll go through an example. I'm going to go through a couple toy examples right now. And so first, just, redefining this supervised learning. It's used for making predictions from a set of input and output data. And so here I've shown the machine learning model as this black box, and you'll see this kind of structure throughout the rest of the talk. But what you're doing is you give the model the inputs, you give the model the outputs, and it learns some statistical relationship between X and Y. And we're going to look at the two different types, classification and regression. A very common classification problem is image classification. And so in this case, you feed the model a bunch of inputs in the form of images and labels. And what I mean by labels is you tell it what each image is. You give it a picture of a cat, you say cat. You give it a picture of a fish, you tell it this is a fish. And so it sort of starts to learn different features of these different images, what a cat looks like. Maybe it recognizes the ears, the cute little nose, the whiskers, and it starts to learn what the different images look like because you've told it what these images are. And so at this point, you have a trained model. Your black box is now trained, and you can feed it an image it's never seen before. And it will predict what this image is. And it does this by giving the probability that that image falls into each of the classes, meaning the different animals that it's trying to predict. And so if it gets an image like this, it might be pretty confident that this is a cat. And so say, 97% chance this is a cat. But if it gets something like this, it might have a bit more trouble. It might say, okay, I recognize cats have these cute little faces, but deer have antlers, fish have scales, butterflies have wings. And so it's going to give different probabilities to those different classes and be less confident in its prediction. So that's classification models. We also have regression models. And so now instead of predicting a class, regression models predict real continuous values. And as data scientists or people who work with data, we might be more familiar with something like this, where we have all of our data points. You can imagine in Excel, we have our column of X's, our column of Y's, the two variables we're looking at. We can plot Y versus X, the orange dots here, and we can ask for a line of best fit, which this is the model. And so this linear regression is actually a form of machine learning. It's one of the simplest forms, and we'll sort of use it to build up our understanding of a bit more complex models. And so when we build a linear regression model, what the model is really learning is the slope and the intercept. So if we have the equation for that line, y equals wx plus b, the slope here is represented by w, and the y-intercept is represented by b. And so I'm going to call these the weights for w and the biases for b. And so that's what the model is, these weights and these biases. That's what this model is learning. And so, we have linear regression. We can also have nonlinear regression, where we have more of a squiggly line, and this starts to get us toward the neural network. And a neural network is essentially a big nonlinear regression model. They often look like this. So I've expanded the black box and I'm showing the architecture of a neural network inside of it. We have the different circles, the gray circles. These are referred to as nodes or neurons. And then we have two columns of these circles in this particular example. And these columns are referred to as layers. And we can see that each node is connected to all of the nodes in the next layer. And so now, instead of learning some y equals wx plus b equation, this neural network is still learning a set of w's and b's, weights and biases, but now there's an array of them. So there's a weight and bias for each line connecting the node in one layer to all of the nodes in the next. So each one of these connecting lines has a weight and a bias. And so we get this array of weights and biases, and this is what tends toward this nonlinear system. And it allows us to extract more information from the data and make more skillful predictions. And so we'll look at this briefly in a case study. I have a background in sea ice, so we're going to focus on this is work I did for my PhD. But we had this question: can machine learning models make skillful predictions of sea ice motion? And we focused on the Arctic. And some motivation for this question. You can imagine if you are one of these ships traveling through the Arctic, it might be pretty useful to know where the ice is going to go tomorrow, so you can sort of choose your path of travel for the least resistance. And so in this study, we sought to make predictions of sea ice motion on 1 day timescales. So in that case, we know what our output is. We know we want to predict y, sea ice motion. And the first question that we come to is, how do we choose X? What are we going to predict sea ice motion from? And to do that, we turn to our expertise in the fields. In this case, it's the momentum balance for sea ice. So I know I'm showing an equation. We don't have to look at the equation at all. We can look at this image that is sort of a crude depiction of the ice. And what this equation is saying is that the movement of the ice, the blue arrow, is forced by these different terms. And on these short time scales, we're trying to make 1 day predictions. A lot of research has been done to find that wind actually explains a large portion of that variability of ice motion on short time scales. So the main driver of ice is the wind. And you can imagine, just a simple example, if you put ice on top of water in a bowl and blow on it, the ice will move. And so that's sort of the wind forcing the ice. And so that chooses us to pick our input. Our input is wind. We're going to predict sea ice velocity from wind velocity. And in this case, we used data from satellite products to represent sea ice velocity in the Arctic, and reanalysis products to represent wind velocity in the Arctic. And so we have these gridded mapped products of these two variables, of our inputs and our outputs. And at the bottom of this slide, we can see this purple strip, and this represents the different phases of building a machine learning model. And so first we have this train validate phase. And in this phase, we take all of our data and then we subset it. We take about 90% of it and we feed it to this black box model. And so we're feeding it the inputs and the outputs, and it's learning some statistical relationship between wind velocity and ice velocity. If the wind is doing X, the ice velocity is doing Y. If the wind is doing A, the ice velocity does B. And so it learns some interaction there. This is the training phase. And so now the model has learned all of those weights and those biases, connecting all the nodes of the different layers. It's learned this interaction, and we move to the test phase. And in the test phase, I said for training, we took about 90% of our data to train this model. And so we have about 10% left that the model has never seen. And so now we know our inputs and we know our outputs. We can feed our inputs to the model and ask it to make a prediction of the output. And then we can compare what the model predicted with what the output was actually supposed to be, what the known value of the output is. And we calculate some metric of performance of how well it made that prediction by looking at different functions of the difference between what the model predicted and what the model was supposed to predict. And once we are, secure that our model is skillful, we move to this actual predict phase where we don't know what the ice is doing tomorrow. We just feed it wind and we get a prediction of ice. And so just sort of, building up from that. Again, we're looking at a linear regression example. When we train this model, we're learning these weights and these biases. What do we need to multiply the wind by in order to get the sea ice velocity? And moving up to a neural network. Now, again, this model is learning a weight and a bias for each of these lines, a node to the node of the next layer. And then so this is sort of one of the simpler forms of a neural network. There are many different types of neural networks. And one that is commonly used in our field is called a convolutional neural network, a CNN. And CNNs work really well with images or image-like data sets, such as these gridded mapped products that we often see. And the reason being is that they have this spatial filter, which moves over different spatial points and looks at now these interactions between the spatial points. And so this gives us some non-local information in addition to the non-linearities that we get from this neural network with these multiple layers and multiple nodes and connections. And so, it's really saying how is the wind at, a given location and all of the neighboring locations used to predict sea ice velocity. So it allows us to draw more information from that data. And so in this study, we compared a linear regression model to a convolutional neural network. And, we trained both of these models, and then we went to this test phase where we're going to calculate the performance by asking the model to make a prediction from data it's never seen and comparing that prediction to what it was supposed to predict. And we do that. We calculate the performance there are many different metrics we can use. Here we used the correlation. So it's the correlation again between what the model predicted and what it was supposed to predict. One would be these are perfectly correlated. The model predict perfectly everywhere. A 0 would be no correlation whatsoever. And so in this first image, we're looking at the correlation of the CNN throughout the Arctic. And we can see that it did pretty well. The correlation was above 0.8 at most locations throughout the Arctic, some decline in skill in some coastal regions. But overall, we were pretty happy with the skill of this model. The second image is the difference in performance between the CNN and the linear regression model, where red is where our convolutional neural network did better, and blue is where the linear regression did better. We mostly see red in this image, which means, for the most part, these more complex models that were incorporating nonlinear and non-local interactions were able to draw more information from the data and make a more skillful prediction than a linear regression. And so, sort of a summary of the work we did here, we found that yes, machine learning models can make skillful one-day predictions of ice motion. And so we've talked a lot so far about what the machine learning model is learning. It's learning those different weights and biases, the W's and the B's, connecting all of the nodes of the layers. But now we're going to get to this question of how is it learning these? And so we'll go back and build up again. Say we have some y as a function of x, say sea ice velocity as a function of wind velocity. And the question is, how do you predict y from x? And we've talked about one way you can do this is to draw a line of best fit. The purple line is the linear regression model, where this model has learned the weights, the W's, and the biases, the B's, or the slope and the intercept. But how is it doing this? And this image here shows us what's going on there. So we can see that between each data point and the model, so between each orange dot and the purple line, we have this gray line, which represents the error of that particular data point from the model. And so we're going to call this E sub I, the error of an individual point. And each point, it has one of these errors. And what happens in this linear regression model is the model optimizes the weights and the biases, the slope and the intercept, by minimizing the sum of all of these errors. So it draws this line so that the sum of all the errors is minimum. And this is called the loss function. There are many different types of loss functions. In this case, we're using something called the L2 norm, which is the square root of the sum of all of those errors. So it takes all the errors, it squares them, sums them, and takes the square root and minimizes that number. So it draws the line to have the minimum of all of these errors. And a very similar thing is done in a neural network case, except it's a bit more complex. So now we still are going to have these errors between each one of these dots and our model. The model is going to be nonlinear, so it's going to have some curvature. And this neural network is going to learn all of these weights and these biases by minimizing some loss function. And it does this through an iterative process that we call gradient descent. And I'm not going to go into details of gradient descent. I just mention it because if you look further into machine learning, you will come across gradient descent. But we'll talk a bit about the iterative process. So here in this model, I have this term G, and G is representing that array of all of the weights and the biases that, again, connect the node of one layer to all of the nodes of the next layer. And so if we sort of zoom out a bit, I'm going to give an overview of what's going on. So we have our inputs, and we have this X sub I here. We have our true outputs, this Y sub I. And initially, when we start a machine learning model, it's going to pick a random set of weights and biases. And what it's going to do is it's going to take its inputs, apply those random weights and biases, which are represented by G here, and it's going to make a prediction. And then we've given it what the Y was supposed to be, and so it's going to compare what it predicted with what it was supposed to predict and calculate the loss function represented by J, which is some function of the difference between what it predicted and what it was supposed to predict. And then it's going to apply this gradient descent, which we're not going to go into details. But what it does essentially is it goes back to the neural network, this function G, and it updates all of the weights and the biases so that the loss decreases and the prediction gets closer to what it was supposed to be. And then it makes another prediction with these updated weights and biases, calculates this loss function, updates the weights and biases, makes another prediction, calculates the loss function. So it sort of goes in this iterative circle, updating these weights and biases, calculating the loss, and trying to minimize that loss function. And each time it goes through this process is called an epoch. And so we are now going to play with this in a toy example called the Neural Network Playground. So in a minute, I will put the link in the chat, but really quickly, I want to go over what we'll be looking at. So on the right side here, we have this image showing the output, where the data is in the circles, and the model is in the background colors. And so our inputs here are the X and the Y axis. There are two inputs, X1 and X2. And then the output is the color, where again, the data is represented by the circles and the machine learning model is represented by the background color. We also have this training loss. So remember this machine learning model is learning all of these weights and biases by trying to minimize the loss. So we want the loss to sort of get near zero. And it does this through this iterative process where it goes through and updates these weights and biases to minimize this loss. And remember, each time it does this is called an epoch. So that's what we have here. And it'll sort of play this forward for us. And then we have something called the learning curve, which is this line here. And on the x-axis, we have the number of epochs, so essentially moving forward in time. And on the y-axis is the loss. And so we can see at the beginning, the loss was quite high. And then very quickly, it dropped off as the model was trained and sort of leveled out at zero. So that's sort of on the output side of things. We also have the internal structure of the neural network. We have the different nodes or neurons, these little squares, and we have the different layers of these. Here, there are two layers. And this allows for different combinations of the input features. And so lastly, we have these features, this column here, which are essentially mathematical combinations of the inputs. And you can think of a feature, say you were asked to draw a circle. And in case one, you are given this feature that you are only allowed to use a straight line to draw a circle. So that's your feature. You have to draw the circle with a bunch of little straight lines. In case two, you are given this feature of a compass. So now you can draw your circle pretty quickly with a compass. So you can think of features as different tools for making this output prediction. In the case of our CICE example, predicting wind from sea ice. Um, these features are actually the first layer of that model. So in this example, this playground here, they've sort of simplified it for us so we can actually toy with the features ourselves. But this would actually be a learned layer in that model. All right, so what we're going to do with this is we can play with a few things. We can choose a data set. There are two different data sets. We can choose features, and we can change the architecture by adding layers or neurons. And then we get to press play. And play is going to run through the number of epochs and sort of train this model to fit the data. And as we're playing with this, things we want to monitor are first the number of epochs, so we can see how many times it's gone through this iterative loop and updated the weights and biases. We want to monitor the loss and the learning curve. So this is, again, the loss as a function of epochs, as a function of how many times it's gone through. And so we would like to see that the loss starts out pretty high and then quickly decreases. And then lastly, we want to monitor the data. And what we really want to see is that the background color, the model, matches up with the data, the circles, the color of the circles. And the intensity of the color, it represents how confident the model is. So if we have a really intense background color in the top and bottom corners, it means the model is pretty confident that down here in the bottom left-hand corner, it's going to be orange. In the top right-hand corner, it's pretty confident it's going to be blue, but in the middle, it's less confident because you can see some blue and orange dots on either side. So with that, I'm going to share the link and I'm going to share a new screen where we will start to play with the playground. The link is coming. All right, so you can all click on this link. And I am going to run us through a couple of examples. So does everybody have the playground open? Just know with this playground, you can't break it. So press all the buttons you want. You can always press the reset button. So what we're going to start with is the first data set. So this data set over here, we'll start with one feature, just X1. And we'll start with one hidden layer. So you can click the plus and minuses and one neuron. And then we press play. And again, what we're monitoring is these epochs, how many times it's iterating through. We're monitoring this training loss, how well the model is predicting the data. And then we're going to monitor how well the background colors match the colors of the circles. And we can see the training loss isn't really decreasing anymore. And at this point, the background colors are sort of doing a good job of matching the colors of the circles, but in some areas they're not. So in the second toy example,
Sorry,
we
Dr. Hoffman. Sorry to
yeah,
interrupt. You only have 10 minutes before
okay,
our session. And thank you.
okay, yeah, thank you. Yeah, so we'll keep the first data set. We will add another feature, just X2, and press play. And so now pretty quickly we can see that the model is the training loss is down to 0. The blue background lines up with the blue dots, and it's pretty confident. So now we'll move on to the second data set. And this data set, as you can see, is a little bit more complex. We have these different blobs. We'll start out with the same architecture setup we have here, 2 features, one node and one layer. We can press play. And we can see that the background colors are very faint. which means the model is not confident. The loss is not zero, and the colors don't really line up. And so this is where we find we need to increase the complexity of our model in order to get better predictions. So we can do this by adding more nodes and layers. Feel free to add as many as you want. Just play around with it. At this point, we're sort of going into free play with this. So yeah, add layers, add neurons, and look at, again, how this training loss goes towards zero, how well the background matches up with the colors of the dots. So adding layers and neurons will help with this, but also adding different features will help with this. So remember, this is different tools we can use, like straight lines or the circle to draw the output. And we can see how that allows the model to sort of converge on a solution. So yeah, I will let you play with this, and just want to end with a final slide giving an overview of what we talked about. So the take-home message here was that we answered the question, what is machine learning? Machine learning models learn these statistical relationships within the data in comparison to numerical models, which are based on these sort of prescribed physics. There are different types of machine learning. We focused on supervised learning in the form of regression using neural networks. And then lastly, this question of what is the machine learning and how? Machine learning models are trained to learn the weights and the biases by minimizing a loss function. And lastly, I'm just going to post another link in the chat. If you want to learn more about machine learning, Google has some free courses. This is just a link to my GitHub, but there are some links there. So yeah, with that, thank you. And I open the floor for questions.
Yeah, thank you, Dr. Hoffman, for the informative session. So we do have few questions in the chat box. So let me read the question. So the first question, can you make any recommendation about the size of data set appropriate for this approach? And what is the minimum sample size?
Yeah. I don't know if I know an exact number for the size of the data set, but I would say I've trained, it depends really on the complexity of the problem. Um, I generally, I guess for the data sets I've built, I've tested different sizes of data sets, and I found that around 1,000 data points, the skill really starts to improve. But generally, with machine learning, the skill is always improving with the more data that you give it. Whereas something like a linear regression might sort of level out at one point if you keep giving it more data. But yeah, I think in using like daily data, that typically works well from observations, but longer timescales is harder from observations because we only have so many years of data.
Yeah, thank you, Dr. Hoffman. And we have another question. Do you have any recommendation as to what model that we can use if extreme event or layer are actually, for example, like heat wave, floods, droughts, and so on, extreme air pollution?
Yeah. So that is one thing that machine learning models are one of the challenges is extreme events, because generally they're learning these statistical distributions, which are for more common events. I don't know of a specific machine learning model, but I know there's like extreme value theorem. There are a couple other statistical methods that you can use for those extreme cases. I think. Oh, I forget the name of this. Yeah, I'll leave it at that.
It's okay. Maybe you can share with us later. And for the
Yeah.
third question, the selection of input variable and model types are quite important for the application of ML models. So which one do you think is more important and worth it, more effort?
I think that The input variables are very important. I mean, like as you said, they're both pretty important. But if you don't choose the correct input variables, your model won't learn valuable information. It won't have, no matter what you choose your architecture to be or the number of nodes and layers, if the input isn't statistically related to the output, it won't be able to learn that interaction. There is a thing called feature selection where you feed it a bunch of different features, you run it through a neural network, then you take one feature away, run it through the neural network. By features, I mean input variables. And you sort of see how the performance changes by adding or removing different input variables, and this gives you an idea of how important those are. Yeah.
Okay. And this is the last question. So is there a way to know how many neurons and layer we should use in a machine learning? Or is it solely based on trials and errors?
They do have algorithms for this now. So when you build one of these models, typically you use a package. There are a few different ones. PyTorch and TensorFlow are the main ones within Python. And within these packages, there are a bunch of different functions. And one of the functions is called a genetic algorithm. And it's, you write one line of code, apply genetic algorithm, and it sort of goes through and chooses the best number of nodes and layers for your problem. You can also do it manually. I kind of like to do it manually just because then I get more intuition for what's going on. As a scientist, we like to know why. But you can use these algorithms as well.
All right. Thank you. Thank you so much, Dr. Hoffman and Dina. Maybe you can share the link that you mentioned below in the chat box. And on behalf of the organizing committee, I would like to thank Dina and Dr. Hoffman for sharing their expertise today. And thank you to all participants for your question and engagement. We look forward to see you in the next session, which we have networking with the established scientists. And before that, we will have 10-minute breaks before we can start with the next session. And thank you, everyone. Have a wonderful day.